Hello everyone. In the previous lesson, we discovered something surprising. When ordinary limits fail, mathematics does not immediately give up. Instead, it creates new objects such as lim_sup and lim_inf. Today we are going to see another example of this visually. When infinite appears, mathematics begin to ask a new question. Which structures survive infinite operations? And the answer leads us to one of the most important ideas in modern analysis, sigma-algebra. When students first see a sigma-algebra, the reaction is usually, why would anyone invent this? Honestly, that is very reasonable question, because at first glance, a sigma-algebra just looks like a word collection of sets. But I want you to forget the definition for a moment. Think of a sigma-algebra as a description of information, not information on your phone, not information in the data, information about what you are able to observe. Now let's look at the formal definition. Don't worry about memorizing it. Instead, try to ask, why are these three properties here? The first says the whole space must be observable. The second says if you can observe an event, you should also be able to observe that it did not happen. And the third one is the interesting part. It says our observation must survive infinity many unions. This is where infinity enters the story. Now, let's look at the smallest possible sigma-algebra. At first, this looks completely unless only two sets, lattice. But actually, this is the most important example because it tells us what happens when we have almost no information at all. Imagine a detector. But this detector is extremely stupid. It only has two outputs. Either nothing happened or something happened. That is, no detail, no measurement, no status, no graphs, just yes or no. That is exactly what empty and X looks like. The core set possible view of reality. Now, let's go to the opposite extreme, the power set of X. Every subset is observable. Every distinction can be made. Nothing is hidden. This is like having a perfect measuring device. A physicist would probably love this. Unfortunately, nature is usually not that generous. Think about taking a photo. A blurry image contains very little information. A high resolution image contains much more. The scan itself has not changed. Only the amount of information has changed. This is actually what sigma-algebra do. They do not change reality. They change what can be discussed inside reality. Now we can finally understand this picture. Every sigma-algebra lives somewhere between these two extremes. Small sigma-algebra, little information. Large sigma-algebra, more information. That is not just set theory anymore. This is a theory of information. Most textbooks say a sigma-algebra is a collection of sets. That is correct, but I think there is a deeper way to think about it. A sigma-algebra tells us what questions we are allowed to ask. If a set belongs to the sigma-algebra, the question is meaningful. If it does not, the question cannot even be formulated. That is very different perspective. And this leads a fantastic question. If the power set of X contains all possible information. Why don't we always use it? Why do mathematics spend so much effort construct special sigma-algebras, such as the Borel sigma-algebra? What is wrong with knowing everything? That question will lead us directly into measure theory, and surprisingly, it is also where mathematics starts to discover the limit of observation itself. Thank you for watching. I will see you in the next lesson.